All right, so today I want to finish talking about a couple of things that we started last time on Thursday. So if you recall, in the previous lecture, we talked about pathfinding in the plane and this more general problem of motion planning using Minkowski sums to deal with robots that didn't happen to be just like a single point. And we didn't really get to this problem of rotation, so I want to say a little bit about that. And I also want to talk about sort of some general complexity results for how hard it is to do these motion planning problems. So we saw a little bit of that using the sum of square roots type problem, but it was a little bit abstract, and it's not clear that that's actually a practical problem or not, right? It's more of a theoretical limitation. So today I'm going to talk about some problems which appear to be very difficult both in theory and in practice. So these are some actual tough lower bounds that you run into in motion planning, and there don't appear to be any kind of easy shortcuts to break away from them, right? So these are things which are probably more fundamental than the sort of numerical rounding problems you run into with the sum of square roots thing. So the basic sort of problem that we're going to look at is a seemingly innocuous little thing, right? Which at first won't appear to have much to do with geometry, but will turn out to show up in a bunch of different settings, right? And we've kind of brushed against it a couple of times already, right? But we haven't actually dealt with it head on. And this is this strangely named little problem called three-sum, which don't worry about the name. I don't know where they came up with it, right? No laughing, all right? This is a serious thing. Three-sum is a real problem, all right?
Oh, it is a real problem.
No, don't go there, all right? All right, so three-sum. All right, so I'll just tell you how this works, all right? So get your minds out of the gutter now. All right, so here's the basic idea. We'll say given three sets, A, B, and C, of real numbers, right? Solve the equation A plus B plus C equals 0 for A in A, B in B, C in C. Okay, so that's the three-sum problem. The basic idea is you just want to find if there's any selection of values in A, B, or C independently that will sum to 0, all right? So the simple algorithm for solving this thing is you can just look at every triple of numbers, right? That would take cubic time. So there's a really trivial algorithm, which will basically solve this in order n cubed, where we'll just, by convention, set n equal to order A plus cardinality of A plus cardinality of B plus cardinality of C, etc. All right, so we'll just set n equal to the size of the largest tuple, in a sense, right? Or the size of the largest one of these sets. There's a slightly tricky algorithm. It's maybe not that tricky, right? But it's a slightly better algorithm, which will get it in order n squared. The idea is really simple. All we do is we just take C, stick it in a dictionary, and then test all pairs, right? So we'll basically three-sum fast or whatever, take A, B, C as input. We create a dictionary, and we initialize it with all of the negative values in C, right? So we'll take every value in C, stick it in this dictionary, and then we say for every number A in A, for every number B in B, if A plus B is in our dictionary, which you could check using a hash table and order n time, or using some binary search tree and log n or whatever, then we'll just return the tuple A, B, negative A plus B. All right? And if there was no solution through this whole loop, then we'll just return nil or whatever, some empty value. Doesn't matter. Right? So the complexity of this algorithm, using some efficient dictionary structure, would be quadratic time. It turns out that no one has ever really been able to figure out how to do much better than this. So this is the best known algorithm. Algorithm for 3-sum. And it's conjectured that it's optimal. So conjecture optimal, right? So that's kind of interesting and a little bit weird, right? So we'd have, the sort of like problem. There's no way you can do this faster than quadratic time. And so given this fact, right, if we can find some way that we can take any problem and reduce it to this 3-sum problem, with a fairly low overhead, so say less than quadratic overhead, then we can say that that problem is 3-sum hard. And if this conjecture is true, then we would actually conclude that that problem isn't going to have any solutions which are substantially better than quadratic time. And I will say one other point about this too. This lower bound here, right, that this requires omega n squared time, is actually tight in a couple of models of computation, but they're all very kind of weak models. So the lower bound in the linear decision tree model, which is a very kind of restrictive type of computer, right, where you can only really build gates out of linear functions, right? Tree model is omega n squared, right? So you can't beat this bound in a reasonable, or in this kind of very restrictive model of computation. It's open whether or not this is true for any general computer, right? But in a very kind of limited model, right? This is not even as powerful as a regular Turing machine or anything, right? It's a really kind of weak computer. But in this very weak computer model, the lower bound is hard. And I'll say another thing too. There's actually some weird results here too. So there's there's a more advanced model of computation called this algebraic decision tree model. Or we'll just talk about algebraic circuits. It turns out there's an algorithm in this more advanced model of computers which solves this problem in order n to the 3/2 log n time. But this algorithm is not actually implementable in practice, right? So it's not implementable on a real computer. Not by a real RAM computer, I just mean on a sort of physical computer. So to actually construct the sort of circuit that you would need in order to solve 3-sum for a given instance would require more work than that particular. It would be basically worse than quadratic time to actually construct the circuit. This is just a sort of decision theory type bound. So what this really shows is that proving a hard bound for 3-sum in a general model of computation is probably really tough, right? So yeah, that's sort of some complexity theory information about the difficulty in 3-sum. Right. So we have this pretty strong conjecture that 3-sum probably takes quadratic time in the best case for any reasonable model of computation. And this leads us to this concept of a 3-sum hard algorithm. So 3-sum hard we'll say that a problem capital X is 3-sum hard if it is little o of n squared reducible. If 3-sum, I should say by it, I'll say if 3-sum is little o n squared reducible to x, right? So this is the idea. So if we can basically take whatever problem we started with, embed the three-sum problem into that thing using some very efficient translation, then we would conclude that that algorithm would probably not have any algorithm that's going to be faster than order n squared. So this is sort of the bottom line of this conjecture. We'll say three-sum hard implies omega n squared bound, right? So that you can't do it any faster than n squared. OK? So let's start out with our first example of a three-sum hard problem. And this is a problem that we're going to call geom_base. It's a bit of a contrived problem, right? So this is not something that you usually see by itself, but this will help in reducing many geometric problems to three-sum. So here is the idea for geom_base. All right. So we're going to say given three sets of points on the lines x, we'll set it like this. We'll set y equals -1, y equals 0, y equals 1. Do any, we'll say are any three of them collinear. So I'll draw a picture of this, and we'll see what it looks like. So let's say we have one line here. This will be our line y equals 1. We'll have another line here. This is the line y equals 0. And finally, a line down here, y equals -1. All right, so we'll now draw a bunch of different points on these lines. Right. And so the question is, if we're given the set of points on these three lines, is there any three of them which happen to have a common line passing through all of them? So does there exist such a line? That's the puzzle. And this problem is, or it turns out that we can take any instance of three-sum and reduce it down to this problem in linear time. Here's how this works. So if we have 3 points, let's just label them here on this diagram. Call them, say, for short here, this will be the point A1. This will be the point B0. And this will be the point C-1. Then we can write the orientation test for these 3 points as a matrix, right? So there's basically A1. So this is basically the same thing as checking if the determinant of this matrix A11, B01, C-1, 1 equals 0, which, if we expand it all out, that gives us this equation -a plus, let's see, should be 1 minus 1 plus 2b plus, or minus 2c equals 0. So we can basically use this rule where we'll map our initial point sets here that we start with. So we'll basically set A maps to the set of pairs -A1. We'll set B, or we'll map it to -2 times A. B will just map to B, and then 1 or 0, and then C will map to -C, -1. Right. So if we apply these rules, we can basically reduce three-sum in just linear time to an instance of geom_base. So the conclusion of this is that 3-sum reduces, we'll write it like this, n to g on base. I hope I wrote those arrows going the right way. It's either that way or the other one. I think they actually go the other way. Something like that. All right. Anyway, so this just means, I hope I wrote the arrows correctly. I always get the direction mixed up for this notation, so I'm now kind of second-guessing myself if I have dyslexia. But OK, basically 3-sum reduces with n over, or 2g on base, right? So g on base is, in a sense, at least 3-sum hard. So any algorithm for solving g on base is going to probably take at least quadratic time. So all right, that in and of itself is maybe not too weird, right? But g on base is not too far off from a variety of other interesting problems that we'll encounter, and we have already encountered perhaps in some form or another. So I'm going to erase this little chunk over here. All right, so keeping this g on base on the board, one small step from g on base is this problem of detecting degeneracies in a point set. So we'll call this problem here is degenerate. This is the problem where, given a set of points, are any 3 collinear, right? Because if we have a set of points where some triple of them happens to be collinear, that would be a degenerate tuple in our point set. So testing if a set of points is degenerate is as hard as g on base, right? And we know g on base is as hard as, or is at least as hard as 3-sum. So we have this sequence of reductions here where we can go from is degenerate I guess I'll write it like this. I'll put 3-sum at the top. This problem can be reduced down to g on base. And g on base can reduce down to is degenerate. And similarly, we can consider this problem of finding a minimal area triangle. So we'll call this problem minimum, or let's just call it smallest triangle. So this is find the triple of distinct points whose triangle has smallest area. All right. So if we can find the smallest triangle, we can definitely test if a set of points is degenerate. All right. So this problem is degenerate, reduces down to the problem of finding a smallest triangle. So we've already kind of seen this a little bit before, right? So remember when we looked at this problem of finding the closest pair of points? That's kind of like the problem of finding the smallest segment, which is sort of a lower dimensional version of the smallest triangle problem. Similarly, detecting duplicates in a set of numbers, that's the same as this is degenerate problem in lower dimensions. So this is sort of just the 2D version of those two problems, right? So it turns out that 3-sum is related to a bunch of these problems in plane geometry. And for each of these problems in plane geometry, no algorithm which runs faster than order n squared is known. So these are basically these problems for which there is no improvement over n squared. And many of these just have to do with checking whether or not your data was even correct to begin with. So if you could run some more general algorithm, you'd have to first maybe test each of these conditions first, right? So these are somewhat tricky problems, right? So let's now move from these sort of robustness problems that you might need to verify to a few more maybe concrete types of issues. And the first of these, which turns out to be very important in the construction of BSP trees, which sadly we don't know if we'll get to in this course or not. But this is the problem of finding a separator for a set of line segments, right? So we'll call this problem separator. So given a set of line segments, is there a line which partitions them into two non-empty sets? So I should also point out that each of these is a linear time reduction, right? So how do we do this? Well, one way to think about this problem, right, is that, or one way to look at this is that we can actually, or well, let me first draw a picture of this to explain what this problem actually involves. So suppose I have a set of line segments like this, another set here. Then a separator would be some line like this, which cuts these two sets of line segments. So this would be a separator. But not all sets of lines are separable. So for example, if I take something like this, then this would be not separable. So the simple algorithm to find a separator consists of just looping over all pairs of endpoints with these line segments and then just checking if that partitions the lines into two sets. Now, that would be cubic time if you did it trivially. You can shave off the n cubed factor by basically sorting these endpoints and then using a stabbing query, basically, to check when that line segment happens to cut one of the others, right? So the question then is, can you do better than quadratic time? And it turns out probably not, because separator is, again, 3-sum hard. Right, so finding a separator. So let's see how you do this. The way we'll produce this reduction is by a direct reduction of geom-base to separator. So here's the idea. So suppose we have our three lines here initially, right? This will be the line y equals -1. Take another set of points here. This will be the line y equals 0. Whatever, this will be the line y equals -1. So what we're going to do is modify this problem a little bit. Right? So this will not be a linear time reduction. It will be an order n log n reduction. So what we're going to get to is ultimately reduce by n log n to separator. Right? Okay, and the way we do this is we first sort our segments left to right. We find the extremal points, and then we're going to put caps here on the end of our segments. So these will just be like little segment caps stuck at the back. And then what we'll do is we'll draw line segments here, except we'll leave infinitesimal holes around each of these points. Oops. All right. OK. And once we've drawn these line segments with these little tiny epsilon-sized holes, right, you can always make this hole small enough that this will work, then these lines will be separable if and only if there is some triple of points here which are collinear. Because if there was a triple of points that were collinear, then I could just draw some line through them, right? Now this one won't work because there's a line there that will stop it, right? But if there was a point here, if these were a degenerate set of points, then I could continue that all the way out and actually split these line segments into two pieces. So just testing whether a set of line segments is separable or not is three-sum hard, right, by this reduction that I just sketched out here. So it consists of building these like little segments with tiny holes in between them and sticking these caps at the end, right? Because if I didn't stick the caps, I could also just draw a line right through it horizontally, right? It wouldn't work. So to rule out those horizontal segments, I have to put the endpoints on there. So separator is n log n, or geom base is n log n reducible to separator. Three-sum reduces there. So this probably omega n squared, right? Very good bet that it's omega n squared, or at least it's three-sum hard. OK. So now we come to our first motion planning problem that is three-sum hard. So this one we're going to call rotational motion planning. This we'll call it rot plan. So this is planar rotational motion planning. So I'm going to just erase this statement up here. So starting from separator, or actually we'll basically, we won't reduce it from separator. We'll actually just reduce it directly from geom base using the same trick, right? So instead of calling this one separator, we're going to call this one rotational motion planning. So we'll say, given a robot defined by a polygon and some obstacle, is there a path through the space of rotations and translations moving the robot from some start configuration to a target configuration. All right, so that's not a precise statement of this, right? But it's good enough for our purposes because the way we proceed with this reduction is pretty much the same way we proved that separator, or the same way that we reduced geom base to separator. So what we'll do is we'll start with geom base. We draw these like lines as before and build the same sort of setup that we had in the separator case. Then for our robot, we'll just pick it to be like a line segment, right? Like a single, very long line segment, which will be on the order of the length of all of these lines. And then on the bottom over here, we'll draw some big holding pen for our robot to sit in when it's all done, right? So this will just be some large space at the bottom. And then our robot will be able to move through this space if and only if it can find some way to sort of like rotate or translate around and then slide through 3 points and pop out the bottom, right? That's the idea. So it's exactly the same trick as separator, except we're just replacing the line that this robot has to move along with like some arbitrarily long segment, right? So we'll just make the robot like a really long, thin stick. Then the robot will only be able to slide through here if that stick is big enough. How long does the stick have to be? It just has to be this length, right? So the length between the two endpoints over there of this whole cage, right? And there's no easier way for this thing to get through there. So that's rotational motion planning. So that's probably not going to work any faster than quadratic time. And I mean, this would also even be a case where, say, like the Minkowski sum wouldn't even be so complicated, right? Because our robot is like a simple convex polygon. So even if our robot was just a convex polygon, it's still NP, or it's still three-sum hard, right? So yeah. So that's a couple of three-sum hard problems. Now, it turns out even Minkowski sums are three-sum hard, right? So, and I'll explain what I mean by that in a moment. So suppose we don't even care about like rotational motion. We want to just stick with translational motions and then look at how things move around that way, or try to do motion planning in that sense. So here's another problem, which turns out to be three-sum hard. I'm not going to go through the reduction, because I think we've seen enough of these now that you get the idea. This problem is called Polygon containment. The basic idea here is given polygons P and Q, is there a translation? I'm going to draw a box around this thing so it's not confusing here. Is there a translation T such that P plus T is contained in Q? So this would be something like I maybe have some arbitrary confusing shape here, some polygon. I have another polygon here. I want to see if there's some way that I can move this thing by some amount t so that it ends up inside Q. So maybe we'll call this one P. This polygon here is Q. And we just want to move it, check if it's contained inside. All right. So this problem, I'm not going to do the reduction because I'm running out of space on the board, and I don't want to spend too much more time on it. It is three-sum hard, it turns out. Right? You just take my word for it right now, or you can look it up. It turns out that the fact that this is three-sum hard also means that most interesting computations on Minkowski sums are also three-sum hard. And I will go through this very quickly. So I'll basically show the reduction for how this works, right? So this thing you can very quickly turn into the Minkowski sum, since P is contained in, our T plus P is contained in Q if and only if T happens to be contained in this set here, right? If T happens to be contained in this thing called the Minkowski difference of P and Q, right? So what is the Minkowski difference? You can think of it as like the dual of the Minkowski sum. So it's sort of like an erosion of one shape by the other. So the Minkowski sum offsets something, the Minkowski difference erodes it. How is this defined? Well, it's basically the complement of the Minkowski sum. So it's, you take the set complement of P, you Minkowski sum that with Q, and then you take the set complement, right? Actually flip these around, so Q set minus P, Q complement, right? So the idea is that you can think of it as that we take the complement of Q here, we offset that by P, and then we take the complement of that. So another way that we can write this is we can basically say, which actually be, the right way that we should say this is that actually there exists a T in P contained in Q if and only if the origin is contained in Q set minus negative P, right? So that's the result, and that can be computed with Minkowski sums. So the conclusion of all of this, right, is that testing if a point P is contained in the Minkowski sum of any two sets is three-sum hard in the plane. So it's three-sum hard in R2, whatever. I mean, pretty much out of whiteboard space here, right? But that's the idea, right? So if you just want to test if a point happens to be contained in the Minkowski sum, let alone even compute the thing, that's going to be minimal quadratic time in 2D. So all of these results are 2D centric. It turns out that this whole business does generalize to higher dimensions in kind of a predictable way. You just have to replace 3-sum with 4-sum or 5-sum or 6-sum, or more generally, R-sum. All right, so this is kind of the general setting now. So I'm going to erase all of this here. And another name for R sum is linear satisfiability, so linear sat. So the general problem here is, instead of given 3 sets, we'll just say given a 1, a 2, etc., up to a sub r, solve the equation a1 plus a2 plus dot 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 plus ar equals 0 for ai in capital AI. Again, there is a conjecture to go with it that this problem takes omega n to the r over 2, right, or the ceiling of r over 2. And this is the general conjecture. And again, it's true in the linear decision tree model. And open in general. It's also worth noting that if you could prove that this was true, this would prove p not equal to np. So probably really hard to do this. So we'll just say would imply p not equal to np. Personally, I do believe that this lower bound is probably correct, but again, it's probably very hard to prove that this is actually true. But it's a good bet that generally R sum is n to the r over 2 complexity. So that is R sum. The basic generalizations of R sum problems are pretty much the same as what we saw for 3 sum problems. So examples would be degeneracy. I'll just write this out. So I'll just say examples of R sum hard problems. These include degeneracy testing. So basically find a hyperplane that d plus 1 points happen to be coplanar to. So find d plus 1 coplanar points. We'll also point out minimal simplex, again by the same type of reduction, and then higher dimensional motion planning problems. So higher dimensional motion planning / Minkowski sums. So that's that. So that's the general picture over there. Kind of unfortunate that these things don't have any easier solutions, but that's what it appears to be, right? So, OK. Now that's a wrap on the motion planning stuff and 3 sum. So now I want to move on to something kind of different with the remaining time that we have in this class. And this is isosurfaces. Though I should probably say one more thing about motion planning. I'm just going to point out that there are a couple of other alternative approaches. So right now we've only looked at motion planning in 2D. We'll just very quickly say a couple of words about higher dimensional motion planning. And this is actually of enormous importance in practice. I will just give you a couple of buzzwords on these techniques, say very superficially how they work, and not go into too much detail on it because it will take too much time. So this would basically be like motion planning for 3D with rotations, or for robots with many different degrees of freedom. So you have to, like figure out how each joint is going to move. All right, so many degrees of freedom, multiple parts, 3D with rotations, maybe. There's a couple of general techniques. The first are inverse kinematics methods. So if your obstacles are basically algebraic constraints, essentially, then this problem of finding some configuration to move from one point to the other is basically a problem of solving like some big system of algebraic equations. And so you can apply some algebraic method to get a solution to that system. There are other techniques like probabilistic roadmaps. So in 2D, we saw that we could use this tetrahedral, or the trapezoid decomposition to split the space into these like little chunks and then do searching through these trapezoids to find feasible paths. In probabilistic roadmaps, we take some higher dimensional space and we build some random tree that kind of covers this, or some random sampling. And then we connect these random samples together and do the search on this sparse, randomly sampled set of points. And the other, and probably most important one here, are rapidly exploring or expanding, whatever. I've seen multiple ways to write this, random trees. And this is based on high-dimensional nearest neighbors, which unfortunately we didn't get to in this class. So this uses high-dimensional nearest neighbors, or approximate nearest neighbors. That's actually good enough for this. The basic idea is you start from some point, and then you pick any point inside this configuration space, or this high-dimensional space that you're searching, and then you find the closest point and connect it. And so you just keep doing this. So you pick a random point, connect it to the closest point, and you just keep doing this, and eventually you'll basically expand out and cover the whole configuration space with some kind of tree, right? So the general idea for this algorithm is pick a random point, try to connect to closest point on tree. You just repeat until target reached, right? Or time exceeds, right? So this is a very simple way to construct a path. So you could basically imagine that you keep doing this, and then eventually you maybe connect to a final target configuration, and then you just walk along the tree to get there. All right, so that's the high-level, very superficial, not too detailed explanation of this. And there are other variations of these things and more advanced stuff, but I don't think we have time to go into it today, so we're just going to leave that as it is. So that's the higher dimensional stuff. And these things have bounds on convergence, right? I mean, they're not as good as what you can do in 2D, but they're they work, right? And they don't give you necessarily optimal paths. They just give you a path, generally. But today, I think I want to talk about higher dimensional root finding, right? Higher dimensional root finding. Usually in 2 or 3D, right, by higher dimensional. So we'll have some function in 2 or 3D. We want to do that. And these are sometimes called isosurface extraction problems. There are multiple ways to approach this, right? So we're going to look at one particular set of techniques, right? So these would be things that would work for topography or volume graphics stuff, right? So, all right. So here's the idea. So we'll say, given some function f from Rd to R, we just want to solve some equation of the form f of x equals 0. Or alternatively, another way that we could write this, we could think of this as that we're calculating the pre-image of 0. Right? So to draw a picture of this, imagine I have some weird function, right, with like different hills and valleys. This would be maybe like some f of 0, right? So draw maybe a side view of it. Or imagine I have a plane like this, then maybe like this ring here, right, would be some f equals 0, right? More generally, we're going to consider values other than 0. So I'll also say more generally, consider solutions to f of x equals c, right? For some constant value c, right? Right, so these are just sort of like higher dimensional root finding methods. So in 1D, this is kind of straightforward. I mean, sort of like a numerical method type of thing, right? So we'll say in 1D, this is just root finding. And you can use Newton's method, or bisection, right? It's lots of different ways to solve this. So to show what this would look like in 1D, imagine I have some function like this. Then I can have this constant value here, which will be, say, f of x, or we'll call this thing, like, say, y equals c. And then we want to look for these two intersection points, or however many there would be, which correspond to these places where this curve f of x equals c, right? So that's the idea. So there's tons of different ways to solve this. But let's focus on this bisection method here, right? So it's not necessarily the fastest one, but it's the one that we're going to look at today, all right? So the basic idea behind bisection is this result called the intermediate value theorem. So I will explain this. So we have this thing called the intermediate value theorem, which maybe you remember from calculus or not, but I'll just recall it here. So, and I should also point out that this version here is equivalent to the other one because I could just subtract c from both sides, right? So I'm just going to work on this one right now. So let f be some continuous real function. Be continuous. And suppose that f of a is less than 0, f of b is greater than 0, and a is less than b. Then there exists some t between a and b such that f of t equals 0. Here's a picture. So imagine this is our point A. This is our point B. We have some interval here, right? So this is the interval AB. And imagine that f kind of goes like this. Then there has to be some point here, call it t, where f is 0, right? All it just says is that if f is continuous, which means you can draw it without lifting your finger up off the paper or moving it around, then at some point, if it starts at 0 and it ends up, it starts out less than 0 and it ends up bigger than 0, it has to cross this line, right? That's all that says. So many different ways that you can prove it. We're not going to do that today, but just for reference, this is the theorem, right? So if you have a function which is continuous, and suppose you sample it at two different places here, and you know that at one point it was less than 0, and then at the other point it was bigger than 0, then you know that somewhere in between it had to cross. So how do you find a crossing given this data? Well, you can do a binary search, right? So kind of like my marker is dying here. So we'll say, and this is the basis for the bisection method. So given a continuous f and f of a b, or f of a less than 0, f of b greater than 0, can find a root by binary search. This is the process, right? So we start, again, with this sort of picture here. This be A and this be B. So we cut the interval in half. We evaluate f at this midpoint, which is the average of A and B. Then we cut it in half again, at the between the midpoint, right? And we just keep repeatedly doing this over and over again, every time getting closer to the final point. So in linear, in number of bits, steps can number of bits steps slash evals of f, we can find a root. Right? So every time, the way you can think about this is that every time you run one iteration of this, it's like reading one bit out of the root of f, right? And then as we get down here, we will eventually fill up all of them. So for a floating point number, you could do it in like 53 steps or something, right? Which would actually probably be overkill. You'd probably get it quicker than that, but something like that. So that's the idea. So, okay, so for 1D, we can find these things. So how do we generalize this idea from one-dimensional root finding to higher dimensional root finding? So instead of just finding, like, say, a point for some function, we would like to find maybe a surface or some curve in 2D, right? And so let me, actually, before I do that, I should say one other thing. So this will only find one root within a single interval. So what if our function f happens to have multiple roots? I should actually point this out. So one way we could do this is we could take the line down here and then chop it up into a bunch of tiny pieces, and then basically use this intermediate value theorem to detect all of the places where there was a crossing, and then run this search to find the roots within those crossings. Now, I should point out that this is not a flawless strategy, right? Because, first of all, it could miss roots, right, where basically our function happens to be very wavy, right? So if we happen to have multiple roots in an interval, then the bisection will only find one of them. And similarly, if we have a function that looks like this, right, or maybe it crosses but then it comes back out, we would miss these types of roots. So this is only going to detect the roots within these sort of intervals, right, where basically f properly crosses one of them and then we have enough space to do it. But as an approximation, it's a reasonable approach to try to locate these crossings using these samples, right? So, okay, so we do this sampling, we cut it up into these like little spaces and detect them. So how do we do it when we want to do this in 2D? Right. So one way we can think about that sampling process that I just sketched out in 1D is we could imagine that instead of sampling things on some set of intervals, we have a cell complex. Right? So let's say we've got some collection of cells, whatever, just kind of drawing them haphazardly. So, and then these could, maybe continue off, connect to other things. So we'll say, given a cell complex, or a triangulation, whatever, call it C, with of r to the d, evaluate f at the vertices of C. So this is the idea. So suppose, instead of testing this thing on some interval, we're now going to take some more general thing, like a cell complex or a grid or however you like it, right? we're going to evaluate this function at each of these points. And what we will do then is record whether f is bigger than our level set that we're looking at or smaller than that level set at each vertex. So for example, maybe f is bigger here, bigger here, bigger here, bigger here, and then it's smaller everywhere else, right? So each of these points are blue, so they're right. So this would be the idea. So we'll basically test if f is greater than 0, right, or less than 0 at each vertex. So in this setting, right, we can basically evaluate f at each of these vertices. And then using bisection, we can find for every edge where the sign of f was different at either endpoint, some crossing, right? So we'll say for each edge with different sign, we can find a crossing of f, right? So for example, here we have a red vertex and then a blue vertex, so we could find some crossing here, another crossing here on this edge and this edge, continuing here. Something like this, right? So with this information, what we would like to do is turn these crossings somehow into a surface, right? Or some kind of contour that separates these blue vertices from the red vertices. So we'll say that an approximate contour is some cell complex that separates blue, or that separates, I guess I'll just write it as blue and red here, right? So following blue verts from red. That's the idea. So, and there's two ways that we can construct this sort of lower dimensional cell complex, which cuts these two things into different pieces. And these are basically distinguished between primal and dual contours, right? So we'll talk about these two different approaches. So we have primal versus dual contours. Another way that you could also think about that is that essentially these primal methods are going to take the existing vertices here, connect them all together, and then build a new sort of contour from these pieces. So it's sort of like a connect the dots puzzle, right? Whereas these dual versions are going to look at a flipped version. So we'll have to basically find new vertices that we can stick in each of these cells. So it's kind of like a pin the tail on the donkey, keeping with this theme of like children's games. So let's talk first about this primal method, right, or primal techniques. So primal methods. So with these primal methods, what we would like to do is connect these vertices together to form contours. So we want to connect crossings together to form contours. So for example, in this picture, this would be pretty easy to do, right? I mean, they're all just triangles, so we're just going to go draw a line here like this, snap them together. In higher dimensions, you would have like maybe some more general type of simplex, and I could cut it apart. But it gets a little bit harder if our cells might not all be triangles. So if we have general polytopes. So for example, suppose I have a cube, right? then maybe I have some crossings here, 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 here. Right, something like this, right? So I have like maybe multiple different vertices, and now I have like a lot of work to do to try to figure out how to separate all this stuff. Guess I'll draw it like that. Yeah. So where exactly you put this surface and how you connect all these little dots together is a little bit messy. One simple strategy, though, is that we can use convex hulls, right? So here's a simple algorithm. Simple method. Take convex hull of points of all crossings plus points of all crossings and points less than 0, right? So we'll basically take all of the vertices which happen to be, say, red, right? And then all of the boundary points, compute the convex hull of that, and then remove all faces incident to all faces incident to vertices less than 0. If you do that for every one of these triangles, though, it will be pretty inefficient, right? So, I mean, running like all of these convex hulls over and over again could be kind of slow. So what you can do to speed this up is we can basically construct a table based on the sign of each of these vertices. So by convention, let's say that if a vertex is less than 0, we'll set this to, if it's less than 0, we'll set it equal to 1. If it's greater than 0, we'll set it equal to 0, right? So a triangle like this would have the code 0, 0, 0. This triangle would maybe have this code 1, 0, 0. And so we take this number ordering the vertices in some way and then flatten it out into some code word and then look that up in a table, right? So we can pre-calculate this stuff and store in a table. Store in a table. How big is this table? Well, it depends on, first of all, what our cells are going to look like inside this complex, whether they're cubes or simplices or whatever, and what dimension we're going to live in. So for the sake of argument, let's just do it with simplices and then cubes. And this will basically be the table size. We'll do it in 1D, 2D, 3D, and just generally D dimensions. So 1, 2, 3. So in 1D, I mean, OK, there's basically a simplex looks like this. It just has 2 vertices, so there's 4 entries in the table, right? Similarly, in 2D, we have 8. 3D, we have 16. And generally, we have 2 to the D plus 1 entries in this table, because we have D plus 1 vertices. For a cube, 1D, it's the same. 2D, we have 4 vertices, right? So we have 16 entries in the table. Then in 3D, we get to a table with 256 entries because we have 8 vertices. And more generally, it looks like 2 to the 2D, right? So these tables in higher dimensions get very large, right? And at some point, there's a trade-off where it becomes easier to like recalculate it all the time, or else just store it in a lookup table. But for any case that we care about, these tables are, manageable, right? So you can just compute these, store them, done, right? Alternatively, you can also just download a table from the internet, right? Because people have already worked this stuff out and then like store it in your code somewhere. So that's the Primal version. The one problem with this, right, is that these tables get pretty nasty. They're kind of hard to like basically keep track of all the mess that's sitting around inside them. And it doesn't always produce like the prettiest surface, right? So for like 3D or these sort of cubicle cells, like people have different rules that they've worked out, which are modifications of this. You can use those tables to track all the data inside there, right? So those are primal methods. It's fine. They're a way to do this. Any questions about this, right? Or any comments? No? OK. So it's basically just a matter of how we're going to connect these crossing points together to form some kind of cell, right? Yeah. So the other type that we're going to look at, or the other method of extracting a surface from this data, are dual methods. So these are dual methods. And so what these do is instead of trying to compute crossings and then looking where they go, right? I mean, they still will look at the crossing data, right? But instead of trying to connect these crossings on the boundary points, the idea in a dual method is that you try to find a point within the cell that lies on the surface curve and is some representative of a feature. So for each cell, we'll find a vertex here, 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 here. So these are for all cells on the boundary. And then we connect them together. So the basic idea is instead of trying to guess some topology on the boundary points, we're going to try to guess a point on the interior of the cell. So find or just arbitrarily select a vertex in the center of each cell, connect along faces, right? So in the dual method, the topology here is completely determined by where the crossings happen to be, right? So wherever we have a crossed edge, we're going to have to put a face, right? So in 2D, this will basically take an edge and then flip it, right? But in 3D, what'll happen is if we have, say, like imagine we have like an edge here. So suppose this is like being viewed, from the side, right? So imagine this is a cube in 3D. Then this edge will turn into a face, right, in the dual complex, right? So basically, 2D edges just flip into edges. In 3D, edges turn into faces. And similarly, the faces here for each of these dual faces will become an edge in the dual complex, right? So a face turns into an edge. And also a vertex will turn into a cell, and cell will turn into a vertex, right? So that's the general pattern there, right? So the topology is just determined by the dual. The only question then is where we're going to put these vertices on the center of each of these things, right? So just connect using dual, right? Hence why they're called dual methods, right? Yeah. So where to put the vertex? Well, this is kind of the main choice that you have. So in the case of primal methods, there is some ambiguity, or you have some flexibility for how you're going to connect all the crossings together. In these methods, you have ambiguity where you're going to put this vertex. The simplest thing, right, or the kind of dumb answer is to just put each vertex at the centroid of whatever simplex, right? So the dumb method is we can use the centroid. Or we'll think of this as basically like a C0 solution. So in this sort of centroid type scheme, imagine I have, say, a grid. And maybe I have some crossings here, here, here. Then this dual complex would look something like this, right? So it'll create a sort of boxy Minecraft type look, right? So you'll just have sharp corner or sharp edges, but no interpolation, right? So this is just putting the vertices right in the centroid of the cell. A slight improvement over this, or we'll just call this the Minecraft method, right? So this is sort of, for lack of a better term, right? The other thing that you can do, though, is we can use the crossings that we would have computed, for example, for the primal method, and then take the center of mass of all of them, or basically take the average. So we'll call this taking the average, or using some first order information about this function. All right, so we're actually taking the values of the functions, computing these crossings here, and then we'll just take the average of all the crossings to set the point in there. So this is a variation of a technique called surface nets, right? Which is actually the first of these methods, right? So these dual methods all sort of started with this technique called surface nets, this take the average or use some sort of smoothing of these points is the sort of simplest, easy way to do it. All right, so that's the second way that we could try to guess where we'd put the vertex. A more fancy way, though, is there's actually a method that's called dual contouring. And this uses a linear least squares approximation. Right? So this will basically just use like crossing info, another way to think about it. This uses crossing position. And then this uses a crossing plane. So how does this dual contouring stuff work? The basic idea is imagine I have something like this, right? So I have a cube here. And so suppose that I know I have a crossing here, and I have these tangent lines to each of them. Then what dual contouring does is you can imagine that you take these two lines and you extend them out, and you try to calculate the crossing point for each of the lines, right? So this is basically the point plus this tangent info, right? So we know this plane, which is going to be passing through this point on the curve. Here we have this point in its plane passing through there. So we'll call this plane, like, say, this will maybe be a plane like ax plus by equals c. This one would be, like, say, dx plus ey equals f. And so then you just solve the system of equations, ax plus by equals c, dx plus ey equals f. And that will give you a point there. The problem, though, is that you might have more than two crossings for any one of these cubes, right? So there could actually be like another set of crossings up here, right? It's possible that you could have a crossing on each edge. And so you'll get an overdetermined linear system, right, with many values. So what dual contouring does is it takes this overdetermined linear system and then solves it, finding the point which is closest to the centroid of this cube. So it finds the linear least squares closest solution to the crossing lines. So that just involves solving like a linear system. The other cost to it is that it also requires computing more information about your function than just the point at which it crosses. So you have to actually like find this plane which is tangent to the function that you're sampling at each point. But if you have this tangency data, then it's not much harder to implement this than it would be with one of these other data. It's just getting that information might be numerically unstable, or it might require like more work to pull that out. Right? If you have that data, you should do it. Right? If you don't have that data, then maybe surface nets is better. Or if you don't even have surface nets data, you might as well just do the Minecraft thing and just extract a boxy, mesh out of it. So OK. Yeah, I'm pretty much out of time, which is unfortunate, because there were a couple of other things I wanted to say. I don't know if we'll be able to get to it or not. We might just have to skip it. But so these are the two sort of standard approaches to doing surface extraction in a nutshell. One thing I do want to talk about a little bit is that how you would kind of optimize this. Right? So these are sort of the easy, sort of like low-level, march over a grid of cells or whatever to extract it. There are two basic ways that you can speed this up. The first is that instead of like sampling on a regular grid, right, densely, you can use adaptive methods, right? So I'll basically say, in a quick hurry here, so how to speed up, or how to do this fast. The first technique are adaptive methods, where you basically, instead of sampling on a uniform grid, we sample on some kind of sparse grid, like maybe using a sort of octree or quad tree-like pattern to try to make the samples like more efficient. So this would just sample on a balanced octree. So that's one sort of simple way that you can make it a little bit faster. Another way you can do this, though, is say given seed points, you can march. So you can march along the surface. So how does that work? So imagine you have a grid like this. So suppose that I know my points are all right here on the surface, and I'm given some seed crossing right here, then I can just march out in a sort of breadth-first order along these seeds, and I don't have to even look at the rest of the grid. So these basically expand out on the surface along these seeds. So the question then is how you find these seed points. Again, there's sort of two ways that you can do this. You could either just guess one, or you could have someone give you a seed. If someone gives you all of the seeds on the surface, then this is basically optimal in the output sense, because for every output polygon or output point, we will basically visit at exactly one point. So this is optimal given seeds, right? But you have to figure out where these seed points will be before you can start this marching, right? So if you know the seed points, though, this is like the fastest way to get the surface out, because you don't have to visit the rest of the grid. So, and I'm almost out of time here. So I just want to say one thing about how you find the seeds. So there's a data structure that we're probably not going to be able to cover because we're just out of time, called a contour tree, which allows you to find these seeds very efficiently. So it's basically a way that you can pre-process this grid to support fast level set queries, right? The basic idea is that it tracks the formation of these contours in this function as the value of the function increases or decreases. So as we change the level set parameter that we're looking at, we can very quickly find a set of seeds for any level set. So if you want to know more about that, you can look it up, or I'll post some notes. But that, I think, is where we're going to stop for today, because we are out of time.